Okay, so next up we have Shan from the Beijing Institute of Open Source Chip.
Good morning, everyone. I'm Shan Liu from Beijing Institute of Open Source Chip. To those who don't know us, we are working on open source and high-performance RISC-V CPUs. Our booth is number 7, right over there behind Ventana. So feel free to go and chat with any one of us. We have lots of excellent work up there. And today, it's my honor to show you the UnityChip verification, that is open source RISC-V verification at BOSC. Oops, sorry. I'll just enter. Okay, the agenda for today, first of all, I'll quickly walk through the verification background with you. Next, I'll introduce UnityChip verification. Finally, show you some examples to help you understand how it works. Okay, let's start with an important question. How crucial is hardware verification? I believe anyone is on the same page with me. The answer is pretty obvious. So here, I just want to show you some concrete number. These diagrams are from Wilson Research Group Functional Verification Study by Siemens. We can see in 2022, only 24% ASIC design has first silicon success. And the top cause of race bands, which is over 50%, is from logical or functional failures. So my next question is, what is the verification expense? Data is from the same study. We can see 50% to 60% project time is spent in verification. Meanwhile, if we look into this diagram, we can easily tell the demand of verification engineers grows rapidly. Before we get into UnityChip verification, let's start from the traditional hardware verification. Usually, it has costly license and proprietary tool chains. It is also usually closed source, and most of the design is in Verilog, System Verilog, or VHDL. With this information in our mind, we asked ourselves, is it possible to reduce cost and improve productivity, benefit from rich software ecosystem, leverage software developers as hardware verification engineers, gather collaborators all over the world? Our answer is yes. That is UnityChip verification. It allows you verifying chip in an open source manner with any high-level languages you like. To make it clear, our scope here, unit test, functional test. Today, we support Verilator, which is an open source simulator. We also support VCS. In the future, we plan to support more simulators like QuestaSim, ModelSim, etc. So now you may ask, how to make it happen? More specifically, how to bridge RTL and high-level languages. Our solution is Picker. It's very simple. Basically, it exposes an RTL module as a high-level API call. For example, you may need to control the clock and reset in your RTL module. From your software code, it's simply like set clock, assert reset, deassert reset. For example, the step function shows up here. It's a function in Picker that allows you to tick n cycles of clocks. This slide lists the main advantage of Picker. It auto-gens high-level abstraction around RTL modules. The behavior of RTL module faithfully preserved because we are using proven simulator collaboration technology from Verilator and VCS. Again, you can pick preferred high-level languages. I'll give you a simple example. On the left side, it shows a DOT, that is a random number generator in RTL. On the right side is the TB in Python. The code is quite straightforward. Firstly, we instantiate our DOT. We identify the clock. Then we assert reset, tick clock. The step function, again, I just mentioned, that is the function in Picker you can use to tick clock cycles. Here we tick 1 clock cycle. And we deassert reset, we tick clock again. In this for loop, it basically runs whatever number of test cases you want. And we compare the results from the DOT against the reference model. If there is any mismatches, it asserts errors. Now let's move to another use case. Let's say we are experienced with UVM, and we want to continue leveraging it. But for some cases, my DOT may be very complicated. It's really hard to design our reference model in RTL. Life could be much easier if we can use, for example, Python to write our reference model. So that is where Picker shines again. We have this Picker transaction that enables the communication between UVM and our Python code, for example. I'll give you an example to illustrate how it works. It's a little bit complicated, so I'll try not to confuse you and illustrate the high-level ideas here. So on the top right corner, it shows how we define our Pico transactions. The DOT is just a simple adder here. So we can see we define adder in with data 0, data 1, adder out, that is the summation. So the adder in and adder out are the objects inherits from the UVM sequence item. Then we simply call picker pack command that helps you generate the header files, the .py and .sv files that you need to include in your Python and UVM code so that you can use picker transaction. Next, in your Python code, there are mainly 2 functions you need to define. The first function is receive traffic from UVM. The traffic sent from UVM is actually a byte stream. What happens in Python? The picker converts the byte stream under the hood into a transaction list. So you can simply iterate through the transaction list to get the data 0, data 1, and send it into your reference model. The next function is send results to UVM. Basically, you instantiate a picker transaction, that is the out function here. You assign your submission into the picker transaction and call the 2-byte stream function, which converts the results into a byte stream so that can be consumed in your UVM environment. So to summarize, there are 2 workflows in Picker. Workflow 1, you have your RTL DOT plus the high-level languages. Again, the RTL DOT is simply a software API, high-level API call in your software environment. Workflow 2, you have your RTL DOT plus UVM plus your Python reference model or even Python test bench. In this flow, it retains the UVM benefits as well as simplifies your reference model and TB into high-level languages. Yeah, that's all I have for today. Thank you.
Thank you very much. Do you have any questions? Oh, here we go.
Thank you very much for the presentation. It was really good. Regarding the first workflow, right, just using Picker, is it possible to do constrained random verification like UVM? Is there a methodology around like UVM-like methodology with the picker?
To repeat your question, you're asking if in the first flow, is there something similar as the UVM methodology?
Right.
In the first flow, there is no UVM. You can define your own verification methodology for sure. What we are doing here is to expose a software API so that you can write your Python, Java, C++, whatever software language you like to drive your DOT or as well as your reference model. Yeah. Answer your question.
So yeah, so basically there's no pre-existing libraries, anything that do it already. So it's left up to the.
You can definitely use the library from the software ecosystem. The beauty of the Flow one is that we get all the software ecosystem for free, right? For example, what I show here, the PyTest, or if you use Python, you can use NumPy PyTest for sure, right? Yeah.
Thank you so much for your talk.
Thank you.